Yeah, Camson, everyone. Let's start off. So last thing we did was this. Reversible and irreversible process. So the next thing, second law of thermodynamics. So last time we have completed with the first law. Now in second law, right, we have primarily two things. One is the heat engines and one is the entropy. Now heat engines is removed from the mains portion, but then again, it is there for bits. It is there in your boards. It is also there for advanced. So unless we get the new portion for you guys, right? So we have no idea whether it is there or not. So we will do it just in case. Because it was a last minute change in the mains last year, meaning this year. Others do keep your cams on. So second law has different forms, but we are primarily interested for heat engines. The first one is your Clausius statement. So what this thing says is, it is impossible for a machine to transfer heat from a cold reservoir to a hot reservoir, basically from low temperature to high temperature without external work. Kind of makes sense. You can't make the heat flow from, low temperature to high temperature on its own. But if you can give some work, this is possible. Best example is your refrigerator or air conditioning. So if you provide electricity, you can actually cool, you can remove the heat from your room and throw it out into the atmosphere, isn't it? So you're making the room, which is already cold, into, even into lower temperatures. So if you can give external work, it is possible to transfer heat from low to high, or else it is not possible. A heat engine working between two temperatures in a reversible process cannot be more efficient than a Carnot engine. We'll see what is a Carnot engine. So Carnot engine is something, which follows a specific process called Carnot cycle. It's the name of a person. So basically, the second statement, what it says is, Between same two temperatures, no engine is more efficient than Carnot engine. So indirectly, what it means is Carnot engine is the most efficient engine. So if someone comes and tells you my engine gives an efficiency of 40%, we'll see what is Carnot engine and efficiency. Let's say if Carnot engine gives you 30%, that guy is bluffing you. So even in the most of the best of the theoretical case, you can't get anything better than a Carnot engine. These all are different forms of second law, but all are based on heat engines. Like I said, in chemistry, right, they're more interested in the exothermic and endothermic. So yeah, they said that is more about heat. Here we're more interested about work. So Kelvin Planck statement. What this thing says is a heat engine cannot convert all heat into work in a cyclic process. So what this statement simply means is you cannot have an engine which is 100% efficiency. You cannot convert all the heat into work. So these are some forms of the second law that we use. We also do have based on entropy, but these are the main things. Clear with these things? Now let's see what is this Carnot cycle. Like again, I'm saying like this thing, all this heat engine stuff is removed from the mains. We'll not be doing any proofs and all. We'll just see the main results. Those are the important ones. Turn the page. Any doubt so far? So let's see what is this Carnot cycle. So this person called Carnot, he figured it out. If a heat engine works in a particular set of process, this gives you the maximum efficiency. We have no idea how we figured it out. We'll not get into that part. But let's see what is it. So we have an adiabatic. First one is an isothermal expansion from A to B. Then we have B to C, an adiabatic expansion. There, so A to B, B to C, C to D. The first one, A to B, is a reversible. There, the first word itself, it says it is impossible. Like last time we discussed, a reversible process takes infinite time or infinite steps to complete. So in reality, reversible processes don't exist. But then again, hypothetically, so if you have a reversible isothermal expansion, so in this process A to B, let's say heat Q1 is absorbed. So in the heat engine is taking Q1 heat. At temperature T1. A to B is isothermal, so temperature is T1. And then B to C, it is a reversible adiabatic expansion. Since it is adiabatic, there is no heat transfer during this process. And when you go from C to D, now the volume is decreasing. This is reversible isothermal compression. So in this process, heat Q2 is rejected. So the engine, rejects heat Q2. So this will be negative heat because it is being rejected. And finally, you come back to the initial state by another compression. So what Carnot says is if something follows these four processes, the engine follows this process, this gives you the maximum efficiency. We'll not get into the proof, but it is true. So out of all the processes, these things give you the maximum efficiency. Unfortunately, in real life, we don't use this. Even though this gives maximum efficiency, this thing doesn't give enough power. Like I keep saying, in reality, right, machines and all, what we are more interested is power. Let's say you have a bike or something which gives you very highest efficiency, but it can travel only at a speed of 10 kilometers per hour. Will you buy it? For 1 liter, you can go 80 kilometers. Pretty good efficiency. 1 liter ke you can go 80 kilometers, but it can't go faster than 10 kilometers per hour. No one is going to buy that bike. So what matters is power rather than exactly efficiency. So in this process, the main two results are this. So when you actually solve this, T1 and T2, we get Q1 by Q2 is equal to T1 by T2. So this we get from this Carnot cycle. So just remember that. So in Carnot cycle, the heat absorbed by heat rejected will be equal to the ratio of temperature T1 by T2. That again, we're not doing the proof. The result is more important. Clear? So if anything that follows these four processes, right, we call it a Carnot cycle. Great. Now, if you see the schematic for a heat engine, we have the source, we have your engine, and we have your sink. So think of like the source is a place which is a high temperature. So let's say when you're putting coal into a steam engine and you're burning, so that entire thing is the source. You're taking heat from there. T source, so this is a high temperature. So from the source, the engine takes heat Q1. In this process, it gives you some work W, and the remaining heat is thrown out into the sink. Like imagine that steam engine, all that steam that escapes out, right? All the heat that is being radiated out. So that is Q2. So this is the heat rejected to a lower temperature. This is the general diagram for a heat engine. You take heat from a source, high temperature, you do some work, and remaining you throw into the atmosphere. Now, the efficiency is defined as, you can clearly see from here, whatever heat that is being absorbed must be equal to work done plus Q2, right? And the efficiency eta is defined as the work done by positive heats. So when is the total work done by how much heat you have given? That will be W by Q1, where W is nothing but Q1 minus Q2, which becomes 1 minus Q2 by Q1. And just now we saw for Carnot cycle, Q1 by Q2 is T1. So here T1 is T source by T sink. So your efficiency eta becomes 1 minus T sink by T source. There, these are the two main formulas you need to remember. If you know these two, you'll be able to handle all of the heat engine problems. There, you can copy it down. We are going to use that. Now, if you look at that formula, right, you can clearly see something. If you want 100% efficiency, what should happen? If you want eta to be 100%, T sink should be 0 or T source must be infinity. So higher the temperature difference between the source and the sink, the more efficient you get. So you can't get T sink 0, you can't get T source infinity. So that is the reason one of the way you can say why you can't get 100% efficiency. So tomorrow if someone comes with a bike and says, no, this engine is very efficient and gives you 50%, right? Now look at the temperature of the engine core and atmospheric temperature and apply Carnot cycle. And if Carnot cycle gives you 40% and someone tells you 50%, he's bluffing you. No engine can give you more efficiency than a Carnot cycle, Carnot engine between the same two temperatures. That much we can say. Put it on. That is the main theory there. Let's see a few questions on how they would ask at a mains level, and then also one or two questions on how they'll ask on advanced level. Copied? Any doubts so far? Anything? Great. Let's see a question. There, let's get both of them. Remember direct formula substitution there. There is nothing hi-fi there. There's nothing to think actually. This is the only formula you have to use. Efficiency is 1 minus T sink by T source. Try. I'll give you 2 minutes. I'll show you. Carnot engine is operating between temperatures T1 and T2 as efficiency 1/6. When T2 is lowered by 62 Kelvin, its efficiency increases 1/3. This was a 2011 question. So the catch here is they didn't tell you which one is sink and which one is source. Can you figure out first of all T1, T2, which one is sink and which one is source? Start from there. Right, Ansh. You have one answer. Got an answer? You can type in the chat box here to the co-host. Again, look at the formula we have. So efficiency is 1 minus T sink by T source. Now you're saying you're lowering the temperature by 62 Kelvin. Okay. Now observe here. If you decrease T sink, if T sink decreases, then this negative number decreases, then efficiency increases. If suppose T source decreases, if T source decreases, this negative number will increase. So 1 minus that will decrease. Then efficiency decreases. Now in the question, he's saying when the temperature decreases to 62 Kelvin, efficiency became 1/3. It actually increased. There, that is the first conclusion. Therefore, TU2 is T sink. and T1 is T source. Clear with that? That's the first conclusion. Without that, you can't go ahead with the question. Now he's saying initially the efficiency is 1/6, which was 1 minus T sink, which is T2 by T1. So yeah, that was 1. And then he's saying efficiency became 1/3 when the temperature of the sink decreased by 62 Kelvin. So T2 minus 62 by T1. So this is 1/3. This is 1 minus T2 by T1 plus 62 by T1. But 1 minus T2 by T1 is 1/6. So 62 by T1 is 1/6. So T1 is 372 Kelvin. Then automatically T2 will be 5/6, so 310 Kelvin. There. Check. Is that clear, everyone? So the whole question is main thing to figure out who is T sink and who is T source. Once you know that, it's just a matter of formula substitution. So initial efficiency was 1/6, 1 minus T2 by T1. Then the T2 became minus 62. So 1 minus T2 minus 62 by T1 is 1/3. Eliminate T2 by T1, you'll get it from there. Yeah. Get the next one. Next one is also same. It's actually even more easy. Right, Ansh. Right, Niharika. So at a mains level, right, the questions were really easy on this. Unfortunately, they removed it. %. They asked you temperature must increase by. I just give a number, no? He's not asking percentage, right, Devansh? Yeah, you might be right in terms of percentage, but yeah. 30 seconds more. Get the B part fast. Any doubts on 18A, please ask. Let's see. So he's saying efficiency of a heat engine whose sink is at 300 Kelvin is 40%. So 0.4 is 1 minus T sink by T source. This is 0.6 and T sink is 300 Kelvin. So here the T source will be 300 by 0.6, 500 Kelvin. Now you're saying it became 60%, so 0.6 is 1 minus sink is same, so T source is this guy. Now it is 750 Kelvin. So the change in temperature of the source is 250 Kelvin. बस इतना ही करना था. Easy? Clear, everyone? Let's see the next one. Any doubts on this page? Perfect. Next one. So we have a source here. We have engine 1. Then we have the sink. Sink is a low temperature one by source. And then we have an engine 2. And then we have a sink. Normally in the power plants, right, what they do, initially they have a superheated steam, meaning the temperature of the steam is almost 180, 200 degrees. They use this steam to run this engine. We get efficiency, let's say work done W1. So this efficiency of this engine 1 is eta 1. The heat is thrown out. Now what will happen, the steam which is escaping out, they capture that steam again, right? They reheat it. Now because you're reheating it or doing something, it becomes more easy. Now you use this heat to run the second engine. This gives you some other work W2. This efficiency is eta 2. and then finally it is thrown into the atmosphere. You're getting it? Meaning, just to give an example, let's say this source ka temperature is 500 degrees or 500 Kelvin. Let's say this is 300 Kelvin, and maybe this is like 250 Kelvin. So the last engine won't give you as much work as the initial one, but it works. So actually, they do this in the power plant, and the efficiency actually increases by 4 to 5%. So now, if this is the case, find the efficiency of the whole cycle. So if the first engine coefficient is eta 1, second engine coefficient is eta 2, find efficiency of the combination of these two engines. I'll simply say efficiency of the system. I can put a third engine also, and so on. This W1, W2 are also not given, so that simply works. So you need to figure out. Answer should come in terms of eta 1, eta 2. I think I'll give you 2 minutes. It's a good one. Everyone should try. It's okay if you don't get answers. The main point is that 2 to 3 minutes that I give you, you need to think about all possibilities. Yeah, like I said, W1, W2 are not given. Right? Yeah, that's confusing you. I'll just write like this. Only thing you know is eta 1 and eta 2. I'll give you an idea. Say eta 1 minus eta 2. No, just you got it right. No, Devansh, that is wrong. Let's assume like this. Let's say this is Q1. This is work W1. So this is getting rejected to Q2. The same heat Q2 is being transferred to the next engine. You're getting it. The heat rejected by the first engine is the heat input for the second engine. And this is W2 and this is Q3. So this efficiency eta 1 is nothing but W1 by Q1. This efficiency eta 2 is W2 by Q2. The efficiency of the system is total work done W1 by W2 by total heat Q1. Making sense? The total efficiency of the engine is what? Total work done by positive heat. So you have to eliminate this and bring eta 1, eta 2 here. Now try. I'll give you another minute. Understood what I did? I put the efficiency for the first engine, second engine. This is for the full system. You just can't add eta 1 plus eta 2. The efficiency of the system is the total work done by the heat given. You gave Q1, and W1 plus W2 is the work done. Eta 1 minus eta 2 by nahi aa rahi hai, that is wrong. The final answer, right? It gives you a nice pattern actually. I'll show you then what happens with 3 engines. I'll show you the pattern. Try. Right, Puroja. Ishana, you can simplify that a bit. You will get the answer, I guess. See, so this is W1 by Q1 plus W2 by Q1. So W1 by Q1 is eta 1, and W2, I need to bring Q2 there. Q1 is nothing but W1 plus Q2, but then I'll have a problem there. I need to eliminate W2 by Q2. Let's not bring that. Q2 is how much? Q2 is Q1 minus W1, because Q1 is W1 plus Q2. So I eliminated Q1, so this became Q2 plus W1. I can do this. W2 will be eta 2 Q2 by Q1. This is better. Now Q2 by Q1, this is eta 1, this is eta 2, and Q2 is nothing but Q1 minus W by Q1. So this is eta 1, eta 2, this is 1 minus W by Q1, which is again eta 1. This will be eta 1, eta 2, minus eta 1, eta 2. Check. Why is it only W2 by Q1? What is the total heat you are giving to the system, God? Q1, right? If I take this whole thing as one engine, what is the input? Q1. Q2 is internal. Clear with this? Did you observe how the answer is looking like? It looks like this, a Venn diagram. If this is eta 1 and this is eta 2, what is the area of this? The area of this Venn diagram will be eta 1 plus eta 2 minus the intersection, no? Which is eta 1, eta 2. So using that logic, if there are 3 heat engines, can you tell me how will the answer look like? Basically, I have to find the area here. So this will be eta 1 plus eta 2 plus eta 3. That will be the full all 3 circles. But then again, you have taken these things common, so you have to subtract. Minus eta 1, eta 2, minus eta 2, eta 3, minus eta 1, eta 3. But then you have to add this in the middle again. So plus eta 1, eta 2, eta 3. If you have studied Venn diagrams in school. That would be the efficiency if there are 3 heat engines. The answer would follow something of this sort. Yeah, inclusion exclusion. Basically, we are just finding the total, the sample size. So when you say eta 1, eta 2, you are counting this area in the middle 2 times. So you have to subtract 1 time the area eta 1, eta 2. Clear out, you can continue doing this. So this is how it goes. Result is cool. Any doubts on this? All clear with this? Let's see one more. Clear, na? Surya, Sharman, Arush. Clear. Daksha, Soham, Samsung. Change your name, Ray. Let's see the next one. This would be also a good advanced question. Let's say we have a tank here filled with some hot liquid. Let the mass of the liquid be m, specific heat S, and temperature is 2 T naught. So this is a liquid filled with temperature T naught, and this is insulated. You have an engine here. We have a sink here. Where the mass m, S, and temperature is T naught. So it's a lower temperature one. This is your sink. This is a source and insulated. That means the heat will not remain constant. So now you have connected these two reservoirs with a heat engine. So you take some heat from here, and in this process you get some work. Now tell me one thing, if you're taking heat from here, what will happen to the temperature? Decrease. And if the heat is rejected here, what will happen to the heat of the temperature of the sink? Increase. That means at every instant, as the heat is flowing continuously, temperature of the sink and temperature of the source are continuously changing. Isn't it? That means efficiency is not constant. This is a Carnot engine. Find the final temperatures and find the total work done. So if you operate an engine between a source and a sink, initially the source ka temperature was 2 T naught. Insulated meaning there's no heat coming in, heat going out. If you see in the previous question, right, these temperatures are maintained. When you say sink ka temperature is 300, someone is maintaining it. If you continuously remove heat, temperature won't remain constant, it will decrease. So the 2 T naught is decreasing and the sink ka temperature T naught is increasing. So efficiency is getting messed up. Then what is the final temperature of the system and what is the total work done? Let's get this. This would have been advanced, easy to moderate one, but this would be an advanced question. So every time you take heat from the source and you run the engine, you get some work. Source ka temperature is 1, and the rejected heat will increase the sink ka temperature. The difference is decreasing gradually. Engine is becoming less and less efficient. I hope the scenario is clear. Someone is not clear with the question, anyone didn't understand what's happening, please ask. Try, you got 2 minutes. One thing is clear, you have to integrate. Nahi, Hana. You just conserve the total energy, means there is no work. You just assumed the heat lost by the source is equal to heat gained by the sink, isn't it? That means there's no work done. So while the heat is going from source to the sink, you did remove some of it, isn't it? In the form of work. So you can't do that. I'll give you an idea. See, like I keep saying, always one thing is clear. If the temperatures are continuously changing, efficiency is not constant, we have to integrate. So let's say after some time, let the temperature become T1, right? And let the temperature become T2. In this process, let's say you took a small heat dq1 from here, and in this process you got a small work done dw, and you got a small dq2 here. So remember that formula which we used, q1 by q2, that is valid only when the temperatures are constant. So q1 by q2, which is T source by T sink, right? And that efficiency formula 1 minus T sink by T source. These things were derived, these are valid when temperatures are constant. So you directly can't use them, like, every instant they're changing, so you can't use them directly. So, but what we do in integration, we assume the time is so small. So after time t, let temperatures be T1 and T2. So we can assume the time interval is so small that temperatures almost remain constant. 2T by E near Ansh. Temperatures be T1 and T2. And let dq1 heat flow. Since the temperatures are, very small time, you can assume almost it is in steady state. We can assume it is in constant. Let heat flow from source to sink. Time dt. So now your equation becomes like this: dq1 by dq2, so that is the heat taken from the source by this thing, will be temperature T1 by T2. And from calorimetry, we know dq1 is nothing but ms dt1 minus sign because temperature is decreasing. This is plus ms dt2 because the temperature is rising. This comes from calorimetry. dq is equal to ms dt. So if you remove dq heat from a system, the temperature will drop by ms dt. So ms will cancel, shift d1 here. So we get dt1 by t1 is equal to dt2 by t2. And that negative sign indicates temperature is decreasing. What do you think will be the final temperature? Will it be different for both of them or same? Should be same. Why? If it is not same, the heat will continue to flow till the engine stops working. So finally, when both the temperatures became same, the engine will stop working. So on the page, so the limits would be like this. So minus dt1 by t1 is dt2 by t2. Limits initial temperature is 2 T naught. Let the final temperature be Tf. This is T naught. Final temperature is Tf. Integrate on both sides. This is ln T final by 2 T naught. This is ln T final by T naught. Send that minus inside. This will become ln 2 T naught by Tf. Ln T final by T naught. So we get from here T final square is equal to 2 T naught square. T final is root 2 T naught. That's your final temperature, everyone. You can remove the ln and cross multiply. I skipped a step there. But check out the steps here. I think if you got till here, your job's done. Then it's just a matter of integration. This was the idea there. You can't use that Q1 by Q2 for the entire process, right? But we can use for a small time dt, let that temperature be T1, T2, and from there you can figure it out. Any doubts on this page? Question is still not over. You need to find work done. How do you find that? And this is the final stuff there. How to find the work done. Can I say like this? The heat lost by the source and heat gained by the sink, what happened to the remaining energy? That is the work done, isn't it? The balance. Let's say if source lost 100 and the sink gained 40, what happened to the remaining 60? So work done must be heat lost by source minus heat gained by sink. This would be ms 2T naught minus T final root T naught. Because you're losing, initial temperature will be more. This is ms. This would be root 2 T naught minus T naught. This would be ms T naught 3 minus 2 root 2. There, this is the work done. Yeah, right, Vihan. You want efficiency? Work done by the initial heat given. You can do that also. Clear with this. This would be an advanced type of question, would be of this sort. Because main scale questions are pretty lame on this thing. They can't really ask too much. Clear, everyone? Clear? Next thing. Now, the reverse of a heat engine is your refrigerator cycle. So we do in the reverse of this. So we have a source, we have an engine, we have the sink. So in a refrigerator, what you do, and let's say this is also a Carnot engine, you take heat from the sink. To do this, you need to provide work. So think of an AC, air conditioning. So if you treat this like your AC, so sink will be what? Your room. That's a low temperature. So your AC removes heat from your room, which is already at low temperature. To do this, you need to provide electricity. That is your work. And all this heat is thrown out into the atmosphere. Did you ever, went and stood beside your outdoor unit? It's pretty hot. It gives out a lot of hot air. So all that is rejected. So we do it in the reverse actually. So now you tell me, for refrigerator, right, finding efficiency doesn't make sense, right? Because an engine is supposed to give you work and give you work and take heat, but this thing is taking work. So if you use for Carnot cycle, if you still use for Carnot engine, so a better metric would be Q1 by Q2 is T source by T sink. So let me ask you this. Let's say I have AC1, which takes 1 joule of electricity and removes 5 joules of heat from the room. I have AC2, which takes 1 joule of electricity and removes 3 joules of heat from the room. Which is a better AC? The first one, right? It takes less electricity, 1 joule, but gives you out to remove more heat. So a better metric would be something called coefficient of performance. So we don't define efficiency, we use something called coefficient of performance. The symbol is beta, which is the heat rejected, which is Q2 by W. How much heat can you remove from the room per unit electricity or per unit work? The higher this value, the better the air conditioning or refrigerator or whatever. So beta is Q2 by W. This is Q2 by W is Q1 minus Q2. Bring that Q2 down. So this will be 1 by Q1 by Q2 minus 1. So beta becomes Q2 by W, and Q2 is saying is T sync by T source minus T sync. That's the formula you need to remember. So we don't study efficiency for refrigerators, we study something else. How much heat can you remove from the room per unit work? Which turns out to be T sync by T source minus T sync. And again, if you look at this formula here, you can clearly get work done is Q2. We'll get T source minus T sync by T sync. See what happens. As the temperature gets closer and closer to zero, what happens? If T sync becomes zero, what happens? Beta becomes zero. That means Q2 by W becomes zero, means W is infinity, right? The meaning of this thing is as the temperature of the room becomes cold, it becomes cooler and cooler, it requires more and more work to remove the same amount of heat. So as the temperature of the room tends towards 0 Kelvin, the work requires become infinity, which you can't provide. Therefore, the room can never reach 0 Kelvin temperature. This is another way to prove that a body cannot, get a 0 Kelvin temperature. It takes infinite work. Even with the most efficient engine that you have, you're still going to take infinite work, and infinite work doesn't make sense in reality. So this is a reason, when you're switching on your AC, right? Normally people say this thing: instead of putting your AC at 16 degrees, it is better to put it at 24 degrees and switch on your fan. This feels same like 16 degrees, but it consumes much less power. That 8 degrees ka difference mein your AC, right, takes up more than 20-30% more electricity. Getting it? So normally when we come from outside, what we do is put it on 16, we put a blast of air. So even nighttime when you're sleeping, right, instead of putting it 16, it is preferable you put it 24 and put a fan on. That is a reason if you go and buy an AC now, right, from last 2-3 years, if you observe, if you buy an AC, when you switch on the AC, it automatically starts at 24 degrees. So government came up with a regulation. Every AC, when you switch it on, the default temperature is 24. Previously, long back, like 10 years back, when I brought an AC, the default temperature was 18 or 16. You switch it on, it starts with the lowest of the temperature possible. Bill used to be a blast, but yeah. Clever, this copied on that formula. Let's see how they frame a question on this. Again, pretty straightforward on this. 16 plus fan, you can make an ice cream, Arush. People have all weird issues. Uh, yeah, let's get this. First was easy. If you look at this thing here, beta is given 5. He's saying extracts heat from the cooling compartment. So he's talking about this is Q2. So beta is Q2 by W. This is 5. This is 250 by W is equal to 5. And this is 50 joules. So the beta 5 meaning for every 1 joule of electricity, you can remove 5 joules of heat. Now he's asking how much heat per cycle is discharged to the room. He's talking about Q1. How much heat is actually thrown out into the atmosphere. So whatever heat you removed plus whatever work you gave, so that would be 300 joules. Easy. Straightforward. If you know your formulas, the questions are easy. Now, when you see this, people came with some more brilliant idea there. Now, India, it is not really that important, but when you go to, these cold countries like Canada or, Russia or Europe and all, the biggest problem they face, right, is cold temperatures. See, let's say India may summer, right, when the temperature goes to 45. If there is no electricity in your house, what you do? Maximum, you'll open all the windows, right? You will take a wet towel, put it on your face, and sleep in some corner. We will still survive. Getting it? But imagine if the temperature outside is -5 or -10. You will die. By morning, when you wake up, you will freeze to death. Getting it? And people fall really sick. So, and if you actually think about it, one of the reason, if you see now, all these major big civilizations, right, they all flourished near the equator. This Indus Valley civilization, Mesopotamia civilization, Egyptian civilization, the Incas or Aztecs. If you see all these things lie near the equatorial plane, you will find some civilizations, but not these huge empires were never built in the northernmost part or the southernmost part. Because half your problem, half the time, right, you are just surviving from the cold. You don't have that extra resources to build armies and wage wars, right? You really don't have too many resources. So even some of your seniors, right, who go abroad also now, when I talk to them, their biggest complaint is that only, sir, this thing last 2 years back it happened actually. Some of your seniors now were in UK when we were talking, so they were telling, sir, this month ka electricity bill was 800 pounds. I think 1 pound is around 90 rupees. So that's like 72,000 rupees electricity bill. And in that, almost 400 pounds is only for heating the room. The biggest problem they have is, you have to provide electricity for that heating. Now think about it. If you directly use a heater is simply a resistor. If you send current, it gives you heat, right? So if you send, let's say, 10 joules of electricity, you'll get 10 joules of heat. This is 100% efficiency, right? 100% efficiency is still less. There is a much better way to get more heat. And that this question is showing you that. So what we do, this is called a heat pump. Maybe we don't hear it in India because we really don't use it much. But abroad, this is like what we use for AC. For them, heat pumps are like a common thing. This would be the reverse of an AC. Meaning, I'll give you very crude form what it's saying. So let's say this is the room. Let's say outside the atmospheric temperature dropped very badly. Let's say -10 or minus something outside. So you want to keep the room hot. So atmosphere is your sink. So what you do, you put the AC ka outdoor unit inside the room, and you put the indoor unit outside the room. Reverse, right? And now see what happens. So now when you provide electricity, work done, right? It takes heat from the atmosphere, Q2. So what you're doing is you're trying to cool the atmosphere, isn't it? You're putting air conditioning for the world. In this process, you get Q1 into the room. Making sense? Since the outdoor unit produces more heat, right? Instead of wasting that heat, why don't you use that heat to put inside the room? No, this way your room becomes hot source. Making sense? Now, if you look at the previous question, see, for 50 joules of electricity, I'm getting 300 joules of heat, which is being wasted into atmosphere. Means I can generate 6 times more heat. This will give you 600% efficiency. Instead of using directly an heater, which will give only 100% efficiency, here I can get 600% efficiency. Right. So in heat pump, what we're interested is, this is just a concept. We don't have as such in the portion. but advanced they can frame passages or something like that. So just have an idea. In heat pump, we are interested in Q1 by W. How much heat are you giving from the outdoor unit per unit work? So Q1 by W is Q1 by Q1 minus Q2. This is 1 minus Q2 by Q1. So this guy will be T source by T source minus T sink. Refrigerator it is T sink by T source minus T sink. Just to give an example, let's say outside the temperatures are very bad, minus 23 degrees. And let's say you want to maintain the room temperature at 27 degrees. You have to convert into Kelvin. So this is 250 Kelvin and this is 300 Kelvin. So we will get Q1 by W is 300 by 50, which is 6. There. Q1 will be 6 times W. For every 1 joule of electricity, we get 6 joules of heat. That's the meaning of that formula there. So this way you can reduce the electricity bill in a much better way. 600% efficiency. But in real life, you have around 300 to 400% efficiency. That's much better, isn't it? At least your bill will be reduced by 1/4. So this heat pump is something which is a pretty common phenomenon in cold countries. We don't use it in Mumbai. We don't need it because we don't have something called winters don't exist anymore. This year it is still better. Last year it was hopeless. And if you go to Chennai, so there we have only 3 climates: summer, hot summer, very hot summer. So going ahead, these are the 3 climates we'll be having. Clear with this. So there, the 3 things. One is your heat engine. So in heat engine, you're more interested in work. In refrigerator, you're more interested in Q2 by W. In heat pump, you're interested in Q1 by W. These are the 3 things that we have. Clear. Next thing, entropy. Now this we do have in the portion, but again, unlike chemistry, right, we don't really have like too much in detail. It's a parameter which gives the disorder in the system. So in chemistry, right, if you see there's something called Gibbs free energy and all that stuff, and then we don't have that. So the main formula is the entropy ds is given by dq by t. This can be also written as delta S is equal to integral dq by t. Or you can also write dq is equal to tds, which is delta q is integral tds. So this is also area under TS graph. T is temperature and entropy. There, these are the main things to remember. In a reversible cyclic process, the entropy is 0. In an irreversible process, last time I said, in an irreversible process, you don't come back in the same way you go. Delta S is greater than 0. So entropy of a system always increases. Maximum, it can remain constant. You can't decrease entropy of a system. So if you have a TS graph, so the area under this graph gives you the heat. You can put down the thing in the red box. That's it. For physics by entropy, we only have these 2 formulas, meaning it's actually the same formula. We just have these 2 things. Then let's say a question. In a certain process, the heat Q is equal to kT. K is a constant, T is a temperature in Kelvin. Find the change in entropy. And temperature goes from 100 to 200. Let's get this. Remember, this is the formula we have. ds is the dq by t, or delta s is the integral dq by t. Point 0.7 इतना अच्छा नंबर आया. Right, Vihan. The rest of you fell into the trap. Be careful. So dq is k dt. So delta s is integral dq by t, which is a k dt by t. This is 373 Kelvin to 473 Kelvin. Temperature must be in Kelvin. 100 and 200, they look good. But T must be in Kelvin. So this is K ln 473 by 373. That's your answer. Clear. Interestingly, J people, this was actually PYQ type. PYQ, they asked a similar thing. And even J people, they also did the same thing. They did ln 2. And they had to give bonus for everyone. So that question was given a bonus. So be careful. So it's a mistake even J people did. If it did it, there's nothing to feel bad about it. Let's see one more. There's nothing there in the question except that Kelvin ka you have to be careful. This is a graph between temperature and entropy. A, B, C. This is S naught. This is 2S naught. This is T naught. This is 2T naught. Find efficiency of the cycle. Remember, TS class gives you the heat in each process delta Q area under the graph. This is another way to ask. Hmm. So for the first one, if you look at it, A to B, so for A to B, this was the area under the graph. It's a trapezium. So this area will give you QAB, the heat. You have to find the efficiency. You have to find the work done. So how will you get work done from here? So QAB is how much is this? So this was S naught, this was 2 S naught, this was T naught, and that was 2 T naught. So it is half into parallelogram area, T naught plus 2 T naught. The base is S naught. 3 S naught T naught by 2. Now for QBC, the area is 0. There is entropy is 0 since TS is 0. For QCA, the area will be that rectangle below this rectangle, and it is going backward, so that would be minus S naught T naught. Now tell me, in a cyclic process, so work done will be QAB plus QBC plus QCA. Why? In cyclic process, delta U is 0. Thermodynamics first law. Work done, delta Q is equal to delta U plus work done. In cyclic process, delta U is 0. You come back to the same point. That means if you add all the heats, you should get work done. So therefore, work done will be 3 S naught T naught minus S naught T naught, which is S naught T naught by 2. What is efficiency ka definition? Efficiency is work done by only the positive heats. So basically what happened was from A to B, the system absorbed 3 S naught T naught by 2. B to C, it did nothing. C to A, it rejected some heat, and the remaining became work. So this guy is S naught T naught by 2 by positive heat is 3 S naught T naught by 2. 1/3, 33.33%. That is how you find the work done. So actually, if you find area enclosed by the curve, that is the work done, isn't it? The total heat will give you work, but in efficiency, you need to find total work by only positive heats. There, this is how you can get efficiency from an TS graph. Be careful with that. Quite a good question. Most people, they don't understand what to do. They get confused because we are used to solving efficiency for PV graphs or even TV graphs. TS is different. Clear with this? That with that, we are done with thermodynamics, second law also. So next chapter will be heat transfer. We'll start after the break. So take a break, come back by 7, 8. We'll continue from here. Any doubts so far you can ask, or let's go take a break, come back in 10 minutes.
Sir, can you explain the reason on page 66 for why work cannot be infinite?
Why work cannot be infinite, na? Infinite work matlab kya?
You gave an example.
Yeah, see now, this is Q2 by W. If T sync is 0, means W is infinity, right?
Yes, sir. So,
You're
sir,
getting it?
when
So
the
what it means to say is, if you want to achieve T sync to be 0, you need to give infinite work.
so, sir, to release heat into a room which has 0 degree Kelvin, then work would be infinite.
Meaning if the room temperature is getting close to 0 Kelvin, you need to give infinite electricity to remove heat from that. It becomes more and more difficult as the temperature gets closer to 0.
Yes, sir, I got it.
So as you get closer to 0 Kelvin, the requirement becomes infinity, which you can't provide. That means you can never cool the room to 0 Kelvin. When the room temperature was, let's say, 300 Kelvin, if you give 1 joule, when the room temperature was 200 Kelvin, it lasts for 10,000 joules. When the room temperature is 100, it lasts for 1 crore joules. As the temperature goes towards 0, the number tends to infinity. You can't provide that much electricity, right? So it's physically not a possible thing. You can never reach. Infinity is not a number, right? Infinity meaning it doesn't exist. You can't give done. Okay.
Thank you, sir.
Come back by 7, 8. Chalo, comes on everyone. Next thing is the heat transfer. So the entire heat and thermo, right? Thermodynamics and heat transfer, these two are the high weightage ones. Now, from the beginning, right, if you see, we kept on saying heat is being given, heat is taken, heat is absorbed, all great. But exactly how is this heat going from one point to another? So there are three ways heat can be transferred. In three different ways. First one is conduction. Second is radiation. The third is convection, which is removed from the portion. But still, we will see a little basics of it. So there are the three ways the heat gets transferred. So what does this exactly mean? Now, let me give an analogy, right? Others do keep your cams on. So let's say we are in a class and there are like 5 students here. I'm standing here, right? And you're sitting in this last corner. So I need to give you maybe a pen. I need to give you a pen, right? How can I give this pen to you? I can give it to the first person and tell him, pass it on, pass it on, pass it on, pass it on, pass it on. Did you get the pen? You got the pen, right? So this is called conduction. Did anyone move actually? Every student is still sitting in the same place, but the pen has got transferred from me to you. This is conduction. Second case, I throw the pen and you catch it. You got the pen? This is radiation. This is how sun sends energy. Sun is sending energy from to the earth. There's almost 15 crore kilometers without any medium in the middle through photons. Third, I will take the pen, I will walk and I give it to you. This is convection. So the matter itself actually moves to transfer the energy. Is that making sense? Either I can pass it on, that's conduction, right? Or I can throw it, you can catch it, that is photons and radiation. Or I can myself carry the pen to the last bench and I'll hand it over to you. This is convection. Making sense? So that's a simple way of putting like what is conduction, convection, and radiation. Clear with that? No. Let's see conduction. So in conduction, the heat is transferred. So one point to another without the actual transfer of material. This happens due to molecular collisions. Energy is transferred. Due to molecular collisions. How does this happen? Now, when you look at molecules in a lattice, they're always in a constant state of vibration. And we saw from this kTg, so kinetic energy is 3 by 2 kT. So proportional to T. So higher the temperature, the faster they vibrate. So if you take two molecules, let's say this guy is going with U1, this guy is going with U2. And if U1 is greater than U2, and if it's perfectly elastic collision, after collision, what happens? The exchange velocities. This guy becomes U2 and this guy becomes U1, the exchange velocities. This is what actually happens when you touch a hot body. So when you're going and touching a hot body, what you're doing is the molecules of your finger are vibrating at a slower rate, and the hot body molecules are vibrating more rapidly, right? And when you go and touch this, the molecules, right? Your molecules started vibrating. Let me show you, kind of like this. So let's say your molecules are vibrating slowly, and that spoon or something which is pretty hot, which you touched it, is vibrating more rapidly. So after the collision gets over, your hand gum molecules will vibrate more, and the spoon gum molecule will vibrate slower. They'll exchange velocities. You're getting it? So that is what you think it is hot. Vice versa, when you go and touch an ice piece, what happens? Your molecules are vibrating more rapidly, right? The ice molecules are vibrating slower. So your kinetic energy of your molecules goes to the kinetic energy of the ice molecules. So you're losing kinetic energy. Whereas when you touch a hot body, you're gaining kinetic energy. So if someone asks you, right, what is heat at a fundamental level? Heat is nothing but molecular kinetic energy. You're getting it? At a macro level, we call it heat. But if you go at a molecular level and observe, heat is nothing but molecular kinetic energy. If the molecules are moving pretty fast, we say it is more internal energy or it is more hot. Making sense? So that is how the energy gets transferred. So whenever you're touching something, the energy is being transferred due to conduction. Conduction is nothing but molecular collisions. The molecules of the other body are colliding with the molecules of your finger, right? Whoever is going faster, they will become slow, and whoever is going slower will become faster. Heat is exchanged. Makes sense. Now, did you notice this thing? When it is cold, right, and when you go to your class or something, when you touch the wood, it feels cold, but when you touch the metal, it feels even more cold. At the same temperature, wood and metal feels more cold. Agreed? So we humans, right? So when you're touching something and say this is hot and cold, what are you actually measuring? Are you actually measuring temperature? If humans can actually experience temperature, shouldn't that wood and metal at 15 degrees should feel same? But you find 15 degrees ka metal is more cold than 15 degrees of wood. So what we humans are experiencing is not temperature, but the heat transfer. The molecules of the metal are more conducting or more easy to vibrate. So they transfer energy much faster compared to a wood. Making sense? So touching, same way, when you're walking on your terrace or something during hot summer without, sandals, your legs burn. But if you wear sandals, your legs don't burn. Even though the temperature is still the same, the heat transfer is less. Clear? So what we humans experience is not temperature, we experience heat transfer. The flow of heat, how fast it flows. If the heat flows faster, we think it is more cold. That is the reason metal feels more cold than wood at lower temperature. So what is happening if you take the rod and let's say if you start heating it, right? The energy is flowing from left to right. So heat is flowing like this. So what's actually happening is the molecules on the left have higher vibrations. These things are vibrating more rapidly and these molecules are going slower. So when they collide, what will happen? This molecule becomes slower, this will go faster. But because there is a heater, energy is continuously being given. So eventually, all the molecules will have similar amplitude. So these have less amplitude. So as the heat goes from left to right, the molecules on the right also will start vibrating more rapidly. So this is how energy is being transferred continuously in a rod. This is conduction. So end of the day, fundamentally what is happening is collisions. And heat is nothing but molecular kinetic energy. Clear with this? Now we define something called a steady state. Now we always prefer to study when things are like have reached a some kind of an equilibrium or a steady state. So this word is important. We are going to use this a lot. Steady state. You will again encounter this thing in fluid mechanics. We'll encounter this thing in electrostatics. We'll encounter this thing in current electricity. Multiple places. So what is steady state? The property at a point. When I say property, it can be temperature, it can be voltage, it can be current, it can be velocity, it can be anything, any property. So when you say property, this could be temperature, velocity, voltage, current, etc. Anything. It does not change with time. And different points can have different values though. So they can change with position, but not with time. Let me show you what it means. For example, when you see a traffic going on a road, let's say there's a speed limit here. Let's say here the speed limit is 20 kilometers per hour. And let's say here the speed limit is 60 kilometers per hour. And let's say here the speed limit is 30 kilometers per hour. Now the meaning of this is, if you're coming on a car, you're coming in a lorry, you're coming in a motorcycle, I don't care. Your speed at this point has to be 20 kilometers per hour. When you reach this point, your speed has to be 60 kilometers per hour. When you reach here, the speed has to be 30 kilometers per hour. Getting it? So at this point, again, assuming everyone follows the speed limit very strictly. So that same car, when it is here, it is having 20. That same car, when it is here, it is having 60. When the same car is having 30. So the speed of the car is changing. Are you getting it? But if a lorry comes here, speed must be 20. Cycle comes here, speed must be 20. Bike comes here, speed must be 20. No matter which vehicle comes at this point, the speed will be 20. So the speed at a point is constant. But the speed of each vehicle is changing with time. Is that sentence making sense? When the when the lorry comes here, speed is 60. When the bus comes here, speed is 60. When the car comes here, speed is 60. Any vehicle that comes to that point, the speed has to be 60. But when the same bus goes from here to here, the speed becomes 30. So speed of the vehicle is not constant. Speed of any vehicle at a given position is constant. Is that making sense, everyone? This is called steady state. Steady state doesn't mean everything has become constant. It doesn't change with time, but different positions can have different values. So at this point, speed of any vehicle is 30 kilometers per hour. But if you see, speed of the vehicle is changing at different positions. Speed of a vehicle is not constant with time, not constant with But at a given position, speed is constant. Is this clear, everyone? Speed at a position is constant. Think of like this. Ever been through a toll naka when you're crossing this Thane or coming? There's a toll naka. So what is the speed of a vehicle when you're paying that money and getting a ticket? It has to stop, right? Zero, na? Whether a lorry comes or a bus comes or a truck comes, it has to stop for a moment, take the ticket and then go. So speed of any vehicle at that toll naka is zero momentarily, and then again it starts. You're getting it. So speed at a position is constant. Now it is a fast tag. Even then they slow down a bit. Clear? Now same thing. Let's see for temperature how it looks. So if you have a rod here, let's say initially the entire rod is cool, 0 degrees, 0 degrees, 0 degrees, 0 degrees, and 0 degrees. And now you bring a heater and you put a flame. Now what you will notice, this guy temperature becomes 100 degrees. This guy becomes, let's say, 20 degrees. This is still 0. This is still 0. This is still 0. So let's say every second you're giving some 100 calories per second. And by the time it reaches here, you have only 10 calories per second. Here it is 0 calories per second. So heat is not flowing anymore. So what is happening is all the heat that you're supplying is absorbed by the rod to increase the temperature. Did you ever do this thing? If you have a water pipe, water tap, right? And if there is no water initially, let's say water got over, the moment you open this tap, do you think water will come out immediately? First, the water has to fill up this pipe and then come out, right? It takes time. So here, if you see the heat, whatever you're supplying is absorbed in order to raise the temperature of the rod. Heat is absorbed to increase temperature. In this scenario, you can clearly see inflow is not equal to outflow. So that is another way to define what is not a steady state. Inflow is not equal to outflow. Whatever you're sending is not coming out. This is a non-steady state. Because if you observe, temperatures are changing everywhere. Now, if you leave this for enough time, eventually you'll reach a situation where this has become 100, 80, 60, 40, 20, and 0. You are supplying 100 calories per second. Here also 100 calories per second is flowing. Here also 100 calories is coming out. So whatever you're sending, everything comes out. Inflow has become equal to outflow. This is a steady state. Why? Think about it. If inflow is not equal to outflow, that means someone is absorbing the energy. If someone is absorbing the energy, then the temperature will change. If temperature is changing, that means the temperature at a position is changing with time. It's not a steady state. So this is an easy way to remember what is a steady state. Inflow is equal to outflow is called steady state. If inflow is not equal to outflow, it is non-steady state because the temperatures are changing still. Is this making sense, everyone? This is how you can say steady state. Now, some people might think like this, sir, why the temperature is not becoming 100 everywhere? Okay. Ask yourself, suppose if this is 100 and this is 100, what is the temperature difference between them? 0. Will the heat flow? Heat won't flow. So if the heat doesn't flow, where will all the heat go then? If your heating continues and the heat doesn't flow, the heat will accumulate. This temperature will go to 200, na? Then the heat will flow. Are you getting what is happening? There has to be a gradual decrease in temperature. It is like this. When you're building a reservoir, you tell me, how will you build it? Will the water pipeline should be gradually going down, or will you just build a horizontal pipeline? If you build a horizontal pipeline, water won't flow, isn't it? So the thing is that there is a gradual decrease in temperature So this is a mistake people do. They think steady state matlab sab jagah temperature same hai. That is not steady state ka meaning. That could be a steady state, but that is not the meaning of a steady state. That's a special case. Steady state ka meaning is simple. At this point, temperature is 80 degrees. You wait for 1 hour, you wait for 100 years, the temperature is 80 degrees. The temperature at a given point is constant. Each point can have its own temperature, but they don't change with time. This is called a steady state. Is that making sense, everyone? Because I have seen generally people think steady state matlab temperature constant ho gaya, meaning they think everywhere the temperature is same. Any doubts on that statement? That's important thing, steady state, do remember, because we're going to encounter that again in current electricity, fluid mechanics, multiple places. The idea is still the same. In a circuit, when I say it is a steady state, meaning voltages and currents at a point have become constant. So how does this look?
Hey everyone, today I'm going to be showing you the world's fastest heat conducting material. And then I'm going to cut it open and show you what's inside of it and how it actually conducts heat so fast. So first let me show you how fast this thing actually conducts heat. I have two rods here.
So you have two rods there. One is a copper rod, regular one. One is called a heat pipe. Right? I'll tell you what it is made of and all, but they kind of look same.
One of these is just a regular copper rod. Now, copper has a very high thermal conductivity. It's one of the fastest conducting metals there is. And because electrical conductivity and thermal conductivity are related to each other, that's why you see a lot of wires made out of copper, because it can also transfer electricity easily. Heat pipe here and show you how much faster this heat pipe actually conducts heat compared to this copper rod. Okay, so now we're going to try to actually see this heat transfer. So I'll put my copper pipe right here. And then I'll put my heat pipe on the other side here. So when this stuff gets cold, it turns black.
So we can't actually see the heat flow. What we see is this. So this paper which is there, when you put some cold thing, it becomes black. When you put something hot, it becomes red. So that is how you know the heat is flowing or whatever. There you can see it's becoming black when he's keeping ice.
So we should be able to easily see the heat transfer from the pipe to the ice when I stick ice on both the copper pipe and the heat pipe. Okay, so what I'm going to do is I'm going to set ice on the heat pipe and the copper pipe, and we're going to see how fast the heat gets transferred from the pipe to the ice. Okay, 3, 2, 1. Whoa,
Look at the top one.
It just instantly turned it black here.
There, bottom you can see how the heat is flowing.
Slowly moving up the copper pipe. That is awesome.
There. So that is how you can visualize heat transfer. So the heat is, in this case, actually heat is being pulled out from the pipe. This is, so the bottom one is a non-steady state. The upper one has already reached a steady state.
How long it takes to move up the copper pipe. Okay.
Now he's doing the reverse. He heated both the pipes and he kept that sheet. Now see, they're more reddish because they're hot. Now he's going to keep ice. So heat will be removed from inside. Upper one is a heat pipe. Bottom is a solid copper rod.
Okay, we've heated both of them up now. Let's set our ice on. Okay, 3, 2, 1. Look how fast this one turned black. The
look at this
pipe
thing.
Was almost instant.
That's a pretty good way to visualize the heat transfer. The molecules, right, are getting cooled down. So all the energy is being transferred.
Pipe, you can see the heat slowly coming out of it.
Molecular collisions do take time.
So what's really neat with this is by just using the heat in your hand, you can actually cut through ice like it's a razor blade.
There. That's a heat pipe actually. It gets pretty cold also.
So in doing that, it instantly gets cold in my hand. So I have to try to transfer the heat back into it as it cuts through the ice. But it's so cool how it instantly just cuts into the ice when I touch it to it.
So basically, you're using your body heat to transfer and cut the ice.
This is just using my own body heat to cut through this. Look at that.
Let's
Transfer
end
heat
this.
so much faster than a regular copper
So how does
rod.
this heat pipe work
This is a
actually?
magnet. So copper can transmit
So what is inside? He's going to cut it.
Looks like a hollow copper pipe. But let's look
So inside
closer
actually it
and
is a
see what
hollow.
we can see in here.
Inside it actually looks like this. It's a hollow pipe, that heat pipe. So let me tell you how it works. So the copper pipe is fine. It's a regular conduction. But heat pipe, what they do now, they first take a hollow copper pipe. Right? They seal it on one side. Then they put a drop of water inside. And then they heat this. They put some water inside and they heat it. Now, when you heat this, what will happen? The water will become vapor. So this entire thing will fill with water vapor. So you'll put some water and then you heat it to high temperature. So the entire inside will fill with water vapor and the air will be expelled out. Making sense? So you heat it to a high temperature, 200 degrees or something. All the water inside becomes water vapor. And when the water vapor comes, the air will be pushed out. Then they seal it. Now remember, this is still at high temperature. Now they cool it down. Now you tell me, when you cool this, what will happen? Now inside, there's only water vapor and you seal it on both the sides and you cool it down. Water becomes, it will start condensing and it becomes a water droplets. And the remaining space becomes vacuum now. Because you removed all the air, the water vapor was occupying the space. The moment you cool it down, water will condense and become water droplets and inside becomes almost vacuum. Now see what happens. Now inside has become vacuum. Now there is some water droplet here. Now the moment you give heat, this water will suddenly vaporize. In chemistry, if you studied, right, what is boiling point? If you decrease the pressure outside, water boils pretty easily. That is the reason higher the altitude, lesser the boiling point. Now inside it is almost vacuum. There is no pressure. The moment you give little heat, it will suddenly vaporize and you'll get steam. But right side there is a vacuum now. So what will happen? The steam will rush from left to right. And suddenly the whole pipe, the heat got transferred, isn't it? You're getting why it is so fast? The moment you give little heat, it will vaporize, and the right side is a vacuum. The water vapor will rush from left to right, carrying all the heat. So what is this? This is conduction, radiation, or convection? What is this? This is convection. This is not conduction. So heat pipe actually works based on convection. That is the reason it is so fast, meaning the molecules just rush to the right end and the whole thing becomes heated up. Whereas in a rod, you literally have to collide and move. Is that making sense, everyone? That's the concept of a heat pipe. We don't have the portion, but yeah, it looks pretty cool. So there. Now let's get into some mathematical conversion of this. Like I said, we study most of the cases in steady state. So heat flow in steady state. Consider a cylinder of length L. Cross-section area A, and the ends are maintained. At temperature T1 and T2. Now this is completely experimental. So if you have a rod Let's say this is T1, this is T2, and T1 is greater than T2. Heat will flow from higher to lower temperature. So this is your heat flow. This is length L and this is area A. Now you can clearly see here, so dq by dt is proportional to the temperature difference. More the temperature difference, faster the heat will flow. Dq by dt is also proportional to this part of the screen. There is an issue, I guess. Dq by dt is also proportional to area. More area, more heat will flow. Dq by dt is also inversely proportional to the length. The longer the rod, more difficult for the heat flow. So if you combine all this, the formula becomes dq by dt is equal to K A T1 minus T2 by L. We can write delta T is the temperature difference. Normally it is T2 minus T1, final minus initial. So the formula is dq by dt is equal to minus Ka delta T by L. This is a formula for steady state. Let's see what each term means. Have a look at this. Now, let me write down that again. So dq by dt is minus Ka delta T by L. So dq by dt is the heat flowing per second. This is also called as heat current. K is your thermal conductivity. So the physical significance is higher the value of K, faster the heat transfers. So K is the opposite of resistance. So K ka meaning is, so K of the copper is more than K of the wood. That's why when you touch a copper, it burns your hand faster. Higher the K, more easily the heat can flow. So it depends on the nature of the material. If you take insulators, can insulators transfer the heat easily? So K tends to 0. They have a very less conductivity. For conductors, like if it's a perfect conductor, K is infinity. So conductivity of metals is greater than conductivity of wood. So that is the meaning of K. What is A? Area perpendicular to the heat flow. This is important. Generally, people take any area they want, and you should take the area perpendicular to heat flow. We will see a question on this. Similarly, what is L? L is not any length. L is a length along the heat flow. If you guys remember in the foundation, we did this for resistances. L rho L by A in the resistance. L is not any length. We will see. So remember that thing. A is the area perpendicular to the heat flow. L is the length along the heat flow. So it depends on how the heat is flowing. And the negative sign here indicates that the heat is flowing from higher to lower temperature. Now, this is the formula for steady state, meaning inflow has become equal to outflow. But let's say inflow is not become equal to outflow. You can study even that also. Then the formula becomes dq by dt is equal to minus ka. Delta t ka place mein you have dt and del ka place mein dx. Again, the same idea. You take the length to be so small, I can assume it is almost in a steady state for that small section dx. This is the differential form. So whenever you have to integrate, this is the thing which you have to use. This is a differential form. This is valid for both steady and non-steady state. And this quantity here, dt by dx, is called temperature gradient. Anything that changes with position is called gradient there. So the whole conduction, right, we play with this formula only. Have a look at this. Clear? Now, next thing, comparison with Ohm's law. So when you have this rod here, length L, area A, this is T1, this is T2, and let this heat current be dq by dt. So if you look at the equation, dq by dt is equal to ka delta t by L. I can write this thing as delta t by L by ka. You can see the resemblance. So dq by dt, delta t L by ka. This kind of looks like I is equal to delta V by R. This is your current. This is your heat current. Now see, this is one thing about Max. As long as the equations look same, Max doesn't care what you're talking about, right? This is voltage difference. So if you say, no, this is different and that is different, Max will simply say, you called it V here, you called it T here. You just change the symbol. Why do I care what do you want to call? Max doesn't care what it is. This is temperature difference. This is quite a useful thing. So as long as the mathematically the stuff looks same, you can actually use every result that is there. So this is your resistance. So this quantity here, the denominator looks like thermal resistance. So R is the opposition to the current flow. This is the opposition to the heat flow. That means when you have this rod here, length L, thermal conductivity and A, you can replace this with a resistor R, which is L by Ka. This is called thermal resistance. And you can use your entire current electricity, series, parallel, everything you studied in school, everything will be valid. quite a useful concept. Again, we'll encounter this in fluids, and we'll again encounter this in, as usual, current electricity. Clear? So L by Ka. If you remember resistance का formula याद है, rho L by area. Rho is what? Resistivity. 1 by rho is conductivity, isn't it? The rho became 1 by K. Isn't it? Rho is resistivity. Rho is 1 by K is conductivity. So the regular resistance का formula rho L by area, rho became 1 by K, so we got L by Ka. Clear with this? Then, so again, like I said, you can use everything that you studied. So series and parallel. So when do you say two rods are in series? If they have same heat flow per second. So let's say two rods are joined like this. L1, K1, area A1, L2, K2, A2. These can be replaced with two resistances. This is R1, which is L1 by K1, A1. This is R2, which is L2 by K2, A2. So basically, they'll have the same current flow. You can replace this with one resistor. R equivalent, which is R1 plus R2. Makes sense. And when they're in parallel, they'll have same potential difference. In this case, same temperature difference. So if you have two rods like this side by side, let's say L1, K1, A1, L2, K2, A2. This is T1, T1, T2, and T2. Temperature difference is same. You can write them like two resistors in parallel. R1, which is L1 by K1, A1. This is R2, L2 by K2, A2. 1 by R equivalent is 1 by R1 plus 1 by R2. R equivalent is R1, R2 by R1 plus R2. And once you get all this, you want to find the heat flow. Normally what we do, I is equal to V by R equivalent. The same way, you can say dQ by dt will be the temperature difference delta T by R equivalent. Makes sense? You can replace that entire system with one resistor, and you can say heat flow is dT by delta T by R equivalent. Delta T is the temperature difference. Clear, everyone? So series parallel, same thing like what you studied in the 10th standard ka, the stuff. Now, other than this, there's something also called Wheatstone bridge. This we will see in more detail in current, but you need to have an idea about this. Comes a lot. If you have a resistance like this, R1, R2, R3, R4, and R5. Now, if R1 by R2 becomes equal to R3 by R4, now when two resistors are in series, how is the potential difference will divide? Potential divide in the ratio of resistances, isn't it? So if R1 by R2 is equal to R3 by R4, can I say this point and this point will have same potential? Isn't it? Meaning, see, for example, if I take two resistors, let's say this is 2 and 3. What is the potential difference here? They will divide in the ratio of 2 is to 3, no? Series, right? I into R. Same way, if this is 4 and 6, the potential divide in the ratio of 4 is to 6, which is 2 is to 3 only. That means this point and this point will have same potential, isn't it? That points will have same potential. So if R1 by R2 is R3 by R4, then if I call this point A and if I call this point B, then potential at A becomes equal to potential at B. Therefore, there is no potential difference. If there is no potential difference, what is the current in the middle resistor? Therefore, current in R5 is 0. There is no potential difference. If there is no current, then that means it is useless. Therefore, R5 can be removed. So your circuit becomes like this. You can't solve this directly. Huh? That is nothing in series, nothing in parallel. Can you see? Can you tell who is in series and who is in parallel? None of them are in series, none of them in parallel. But the moment I remove R5, suddenly it becomes easy to solve. R1, R2 are in series, R3, R4 are in series, and the upper and the lower branch are in parallel. This is called a Wheatstone bridge. So this by this should be equal to R3 by R4. If this ratio is maintained, you can remove the middle resistor. If it is not balanced, there are ways to do, but we will see them in current electricity. This is called a Wheatstone bridge. So series, parallel, Wheatstone bridge. These three are standard stuff you should know. Clear? Any doubt so far? Let's see a question. We got a cuboid. Let this be A. Let this be B. Let this be C. This is phase 1, phase 2. So the room you're sitting, the left wall is 1, the right wall is 2. The ceiling is 3, the floor is 4, the front wall is 5, and the back wall is 6. So there are 6 phases. So find the ratio of thermal resistance. So depending on between which two surfaces you're keeping temperature, the heat will flow in different directions. So if the temperature is given between 1 and 2, find the resistance. 3 and 4, find the resistance. 5 and 6, find the resistance. Meaning, if I have to show you, it kind of looks like this. So the first one is 1 and 2. So this is 1 and 2. So you're talking about this side and this side. 3 and 4 means this side and this side. So heat is flowing up to down. 5 and 6 is the front face and the back face. Find the ratio of resistances. When the heat flows from 1 to 2, heat flows from 3 to 4, heat flows from 5 to 6. Remember the formula is L by K. Now, this is what I was saying. The people who don't know, right, they will think resistance is rho L by A. They don't know what is L and what is A. All three sides are different. L is the length along the heat flow. A is the area perpendicular to the heat flow. Try, I'll give you a minute. Let's see. So here the heat is flowing from left to right. So the length is A and the area is BC. So this would be A by K BC. Here the heat is flowing from up to down. So this is BC by KAB. This is B by KAC. Multiply and divide by A. So A square by KABC. Multiply and divide by C. C square by KABC. B square by KABC. That goes off. You have A square is to C square is to B square. Make sense? There's much faster way to do. The resistance is L by KA. Multiply and divide by length. Then this guy becomes L square by K into volume. Now, no matter which way you see, volume is constant, no? R is proportional to L square. This is even faster. But you should still know what the meaning of L means. L is the length along the heat flow. Sure, everyone. Clear? So L, A, you should know the meaning. If you just say length and if you just say area, you will be confused like, what are you talking about? Next one. We have a rod here. This is length L. This is K. The radius is 2A. This radius is A. This is also L and this is also K. This temperature is T naught and this temperature is 2 T naught. This here is your interface. Find the heat flow and the temperature at the interface. So how much heat flows from left to right? Find heat per second and temperature at interface. Finish off, last one for the day. 1.80, 90 divided by 5. Yeah, that looks right. Let's see. So step 1, replace them with resistor. So this would be a resistance, this would be a resistance. So let's call it R1, which is L by K. Area will be 4 pi A square, pi to A whole square. For simplicity, let me call this R. Then this is R2 is L by K pi A square. Then this should be 4R. So R equivalent will be R1 plus R2. This is 5R. Then dq by dt is nothing but temperature difference by R equivalent. Temperature difference is T0 by 5R. There you can substitute R, you'll get the answer. I will leave it to you there. Now, this point your temperature is 2T0. Let this temperature be Tx and let this temperature be T0. Now, in both of them, what is same? The current. Now, listen to this thing. This is important. So, current I is what? The potential difference, so temperature difference by resistance will give you the current, isn't it? So, for the resistor R1, 2T0 minus Tx, the temperature difference by its own resistance, R, that is a current, that should be equal to, again, this temperature difference by this resistance should give you this current. And we know these two are equal because they're in series. So Tx minus T0 by 4R. Does that make sense, everyone? I have simply found current in the first resistor, current in the second resistor, and I'm saying both are equal. And what is current? Temperature difference. Current always flows from higher to lower. So for R1, 2T0 is bigger than Tx. For R2, Tx is greater than T0. Initial minus final by resistance. RR gets cancelled, cross multiply. 8T0, 4Tx is equal to Tx minus T0. We get Tx is equal to 90 by 5. Check. Or you could have actually equated this here and you could have solved it. That also would work. Both are right. I would prefer this because without finding dq by dt, I can find current, heat, temperature at the interface. Clear, everyone? There. So that is one. So next class when we catch up, we will do a few more problems there. And next class will be an important one. We will do more higher level problems like we have integrations and all that stuff. So next class will be quite a good one. It will be more variety and stuff. So, and it is an important one because the same logics, same techniques that I teach you, I can use that in current electricity also. So it would help in that way. Okay, with that we'll wrap up for the day. So we'll catch up on Thursday at 5:30 as usual. Right, the test is still online, so do make sure to give it till Friday evening is the deadline. So any doubts, anything, you can stay back and ask. And thermodynamics is done, so do start solving. Right, if you're solving your classes ka material, DCP, HCV, whatever you're doing, do finish it off. So anything, any doubts, stay back and ask also.